welcome everyone for today's seminar. Please be aware of the exit signs in case we need to leave the room if there's an emergency. And for those that are on the internet, we strongly encourage you for the Q&A to send your questions in at first opportunity so that we have time during the Q&A to actually take them. So, Dr. Lashkari?
Thank you, Peter. This obviously is a topic of significant concern, the cool communities, sustainable communities, cool roofs, cool pavements, and urban forestry at the Air Resources Board. And since the passage of Climate Change Solutions Act of 2006, it has been a topic of major concern and major research effort at the board. Thanks to the efforts of our elders and betters such as Professor Art Rosenfeld, ex-commissioner of the California Energy Commission, this topic has been alive for several decades, and the technologies embedded in it are considered mature. The research division of the Air Resources Board has had the privilege of leading this research effort for quite a few years. Our work on cool pavement, our works on albedo assessment are merely the leading edge of this activity. Prior to these works, we had to work with the same principal investigators to try and develop teaching tools, to try and develop databases, and to try and significantly expand the study of science in this area. I should say a few words about Professor George Ban-Weiss. Professor Ban-Weiss is a professor at the University of Southern California, and his education, doctorate degree, etc., was done at the University of California, Berkeley. And his working life before going to USC was at Lawrence Berkeley National Lab. Before further ado, Professor.
Okay, thank you very much for the introduction, Ash. As he said, my name is George Ban-Weiss. I'm an assistant professor at University of Southern California in the Department of Civil and Environmental Engineering. And I'm going to talk to you today about a project that concluded several months ago, whose aim was to look at the albedo of rooftops in cities in California. And we quantified the albedo of rooftops using remote sensing data. So before I get into the meat of the presentation, I want to be sure to acknowledge the team of folks that worked on this project. Pictured at the top is Dr. Ronan Levinson. He's the group leader of the Heat Island group at Lawrence Berkeley Lab, that group has a long history of working on cool communities topics. Also, Jordan Woods, pictured in the middle, was a student researcher who did a lot of work on this project at Berkeley Lab also. Of course, thank you to the California Air Resources Board for sponsoring this work. And most of what I talk about today comes from two publications shown in the slides here. Maybe I should use the mouse pointer so that, working? Yeah, that is working. So the two publications shown there that came out this year in solar energy. So you can get a lot more detail about what I'm talking about today in these two publications. So some motivation for why we're interested in doing this work. The first is that buildings are responsible for a large fraction of total energy use in the United States, something like 40%. And so anything we can do to reduce building energy use is, of course, goes a long way in reducing energy and corresponding greenhouse gas emissions. On top of that, many cities around the US and the globe are so-called urban heat islands, which means that they have higher temperatures within the city than the surrounding rural areas. I'll talk more about the urban heat island effect in a moment and what causes it. On top of that, we have global climate change that is occurring and is projected to warm cities around the globe. And so, again, anything we can do to potentially counter some of those temperature increases locally could be beneficial. And why do we care about climate in urban areas? Well, around 80% of people in the United States live within cities. That was as of 2010, and that fraction is growing. And so any increases in extreme heat conditions, for example, impacts a lot of people. So this figure here is an illustration of the urban heat island effect, and it shows that within urban regions you have temperatures that are higher than the surrounding suburban and rural parts of the city. Urban heat island, the magnitude of the urban heat island really varies depending on what city you're investigating, and not every city necessarily even has an urban heat island effect. It depends on what kind of land cover the city is essentially replacing and the surrounding regions. But in general, I mean, urban heat island effects commonly cause air temperatures to be roughly 3 or 4 degrees C higher within the urban area than the surrounding region, or 7 or 8 degrees Fahrenheit. There are many different ways of quantifying the urban heat island effect. You can use air temperatures or surface temperatures, and actually a lot of complexity to it. But this is kind of the first order look of the urban heat island effect. So as I mentioned before, climate change is projected to warm cities around the globe. Actually, quantifying the local impacts of climate change is quite a challenging thing to do. This figure uses data that came from a study that was just published this year. It comes from Alex Hall's group at UCLA. I think he gave a talk here actually not so long ago on this work. And what this shows is for Los Angeles, and it projects and estimates the number of days per year. Whoops, that was the wrong button to press. Should I press? Oh, good. It shows the number of days per year with temperatures greater than 35 degrees C or 95 degrees Fahrenheit. And if you look at the blue, that bar shows currently how many so-called extreme heat days there are per year. And of course, as expected, there are some parts of Southern California that see more extreme heat days than other regions. Places like Bakersfield and Palm Springs have quite a few number of days above 95 degrees Fahrenheit. And then the red bar above the blue bar there shows the additional number of days above 95 degrees Fahrenheit that are projected in one scenario of how climate change may evolve in the next 40 to 50 years. So it's the additional days by mid-century. And so what you can see is that you have something like 20 days per year increase in a lot of the regions. And of course, from a relative point of view, a place like Bakersfield that is kind of equipped for extreme heat days may not actually have as hard of a time adapting to that as a place like Los Angeles, where that number of days increase is actually like a 3 to 4 times increase in number of extreme heat days per year. And so in regions where there are people that are vulnerable to that, might not have air conditioning, or elderly populations, this could potentially be a big deal. So the point of this slide is to relay the importance of thinking about ways to adapt to climate change. Mitigating climate change in general requires, of course, vast decreases in greenhouse gas emissions and CO2 emissions, and that is a really top priority, of course. Of course, the Air Resources Board is doing a lot of work and is really a pioneer in trying to reduce CO2 emissions and greenhouse gas emissions, at least in this state. But the point of this slide is that, it of course really requires global cooperation to keep CO2 concentrations in the atmosphere at levels around what we have today. And so if you look at the figures at the bottom, what you can see in the figure on the left is 2 just hypothetical scenarios for what CO2 emissions globally could look like over the next 50 years. If you look at this A2 scenario here, that's one projection, one scenario where you have vast CO2 emissions increases, and this is something around what is potentially expected for global CO2 emissions. The blue line labeled W9 is a hypothetical what-if scenario. What if we could actually flatline emissions? And so the point is then, if you look at the figure in the middle, right, even with flatlining CO2 emissions globally, which would be, of course, extremely challenging, you still have global increases in CO2 concentrations of almost up to 550 ppm from 400 ppm that we have today, and consequent temperature increases since pre-industrial up to 2 degrees C or so. And so the point of showing this is that, even with vast decreases in CO2 emissions, there will be some climate warming as projected here. And so it's important to think about sort of local solutions at the city level for countering some of these increases in urban heat. So how can we reduce urban heat? Well, one way is to essentially counter the urban heat island effect. And it helps to know what causes the urban heat island effect. The pie chart on the right-hand side of this figure shows the fabric of a typical city. This one is actually Sacramento, but it doesn't change all that much from city to city. There's some variation, of course. And so cities in general are roughly one-third pavements, one-third roof, and one-third vegetation. And so the pavements and roofs make up an important fraction of a city, and these are impervious surfaces that have certain properties that lead to warming in cities. And so one way of reducing urban heat is to counter the impacts of those impervious surfaces. And so if you look at the left-hand side of the slide, you see methods for reversing the local climate consequences of the urban heat island effect. And the first one is dark surfaces. So dark surfaces lead to urban heating. These are surfaces that absorb the vast majority of incoming sunlight. They heat up in the sun and then transfer that heat into the urban atmosphere. And so to counter that, what you can do is use materials that reflect sunlight rather than absorb sunlight. Cities also, in general, it depends on the region, but in general, in most locations, have much less vegetation than their surrounding rural areas have. And so another way of cooling a city is to, of course, increase vegetation. You can do that at the street level, you can do that on rooftops, and various places. And another way, which is perhaps has less potential, but does have potential, is anthropogenic heating. So use of air conditioners and engines and other things that give off waste heat lead to heating in cities. And so, anything that you can do to reduce energy use in a city, or potentially using, things like electric cars that don't have the waste heat locally, can also potentially reduce heat in the city. So this leads me to describing some cool community strategies. So these are ways of cooling down cities. And the primary focus of this talk is on the first bullet, cool roofs. So rooftops historically have been quite dark. They absorb the vast majority of sunlight, and they transfer that heat again into buildings and into the atmosphere. And so one way of countering that is to use cool roofs. Pictured to the right, you can see a roof with a white coating there. And so a coating like that can reflect 80 to 90% of incoming sunlight. Shown to the right of that is an asphalt shingle, and asphalt shingles are very common in California for residential homes, and those can be made cool also, even without looking white and reflective. I can go into some of the details of how that works a little bit later. As Ash mentioned, cool pavements are another possibility, and this is something that my group in Lawrence Berkeley Lab and UC Davis have been working on in a project that I'll describe later. And what you can see a sort of a, I would say, radical colored cool pavement in a parking lot shown in this figure here. It is made to look somewhat like asphalt turf in this parking lot. Looks quite interesting, actually. And again, an asphalt pavement or any kind of pavement can be made cool and reflect more sunlight. And then vegetative roofs pictured in the middle here. These can add insulation to rooftops potentially, and from an urban heat island point of view, they increase evaporative fluxes to the atmosphere. So these evaporative fluxes, in a sense, act like an air conditioner for the urban atmosphere and can cool that way. And then street level vegetation, very similarly, they increase evapotranspiration, and so they can cool the atmosphere in that way. And they also provide shading and can shade buildings, for example, and reduce the energy consumption of buildings that they shade. So I should introduce this metric, because I'm going to use it throughout the entire presentation, called the solar reflectance. It's also known as the albedo. Those can mean slightly different things depending on what community you talk to, but for the purposes of this talk, I'm going to just assume they're the same thing. The solar reflectance is the ratio of reflected to incident light. And so a material, let's say a hypothetical material that reflects all of incoming sunlight, a very bright material, that would have an albedo of 1. And a surface that absorbs all of incoming sunlight, that would have an albedo of 0. And so, historically, I'll call them hot materials, right? Materials that get warm in the sun, those have low albedo. Cool materials have high albedo. That's okay. So solar reflective roofs can both reduce energy use in buildings and they can lower urban temperature. You get sort of a 2-for-1 with a cool roof in this way. And so first, look at the figure on the right. This is a building that has a dark roof, widely used in the past. And you see the yellow arrow that's pointing downward here. That's downwelling sunlight. And a dark roof like this will absorb the vast majority of that downwelling sunlight, 80 to 90% of it, maybe even a little more. And that means that the reflected sunlight away from the roof is minimal. It's very small. And so that downwelling sunlight is absorbed by the rooftop. It heats up in the sun. And then that heat that it absorbs is transferred into the building, and that increases the cooling load of the building in the summer. And it's also re-emitted to the atmosphere above in the form of sensible heat fluxes and long-wave radiation. On the other hand, if you've got a cool roof shown at the left here, the vast majority of downwelling sunlight can be reflected away. So if a new white roof can reflect 80 to 90% of sunlight away, and that means the roof itself is absorbing a lot less sunlight, stays cool in the sun, and it transfers less heat into the building and into the atmosphere above. And because cities, again, are made up of 20 to 25% rooftop from an area perspective, you can have an appreciable effect on the urban climate by changing rooftops at the city scale. Yeah. Okay, so that's a good question. Where does the reflected energy go? The vast majority of it makes it out to space because the atmosphere is very transparent to shortwave radiation or sunlight. Yeah. So cool roofs reduce energy use in most climates. If you look at studies that have been done over the last 2 decades or so, you can see that in many situations, cool roofs can reduce cooling energy load by 10 to 20% or more. There are some situations where it actually can reduce cooling load by a lot more. There are situations where cool roofs make a negligible difference on the cooling energy use. Also, it very much depends on the construction of the building and how coupled the roof properties are to the conditioned space in essence. The study that I'm citing here and that's pictured here comes from work that was done by Pablo Rosado et al., published last year. And what they did is compared 2 side-by-side homes, nearly identical homes that were basically the mirror image of each other. The home on the left had a cool concrete tile roof with an albedo of 0.5 or so, meaning that about half of the energy from the sun was reflected back to space. And the home on the left had a dark asphalt shingle roof with an albedo of 0.07, so that means over 90% of incoming sunlight is reflected or is absorbed by the rooftop. And what they found was that the annual HVAC energy cost savings, oops, same bad button, sorry, shown at the bottom here was a 20% savings. And so this includes both the cooling energy savings and the heating penalty, right? Because in the winter, you actually want to absorb sunlight so that you, that adds, basically absorbing sunlight is good in the winter, right? And so most studies will account for this, and so the energy cost savings in the end accounts for both the cooling energy savings and the winter heating penalty. And so that's why the slide title says reduce energy use in most climates. It's not true in every single climate, but actually in most climates it is. Cool roofs can also reduce urban temperatures. This figure here comes from a paper that came out last year. It was published in PNAS, where they looked at the widespread implications, the climate implications in the United States of widespread deployment of cool roofs. And this is kind of a complicated figure, but just focus on the bars that in each of these regions that are second from the bottom here. So this one, this one, this one. For all of you at home, let me use the pointer. So this one, second from the bottom, second from the bottom, second from the bottom. And so what that shows is the urban climate consequences of widespread deployment of cool roofs. Okay, and uh-oh. Did I touch something? We'll be back with you after a short word from our sponsors. Sure. Sure. Mm-hmm. Mm-hmm. Yeah. I will. Oh, it's back. Should we save that for the end, or should I? Okay. Okay. It looks like we're back. So, okay. So what this figure shows, so again, look at the boxes from the second from the bottom, and you can see that in, well, the first takeaway point is that the temperature implications of cool roofs in urban areas around the U.S. can vary, so it depends on the region. And that's one thing that we like to say with urban heat island mitigation is that there isn't necessarily one silver bullet way of doing it. It depends on your region. But in almost all cases, you have coolings of the urban area approaching 2 degrees Celsius or so. And so if you look in California, you see that slightly lower coolings, a little less than 1 degree C in the Arizona region, Florida, even smaller, mid-Atlantic regions, 2 degrees C or so. But one thing that causes some uncertainty in estimates like this is that it's challenging to know really what the roof albedo increase that you can attain in a city actually is, right? So the temperature decreases that you can attain using cool roofs completely depends on the albedo increase that you can attain within a city, right? And so that is, of course, and so we actually have a good sense of what the maximum albedo of cool roofs are, just technologically and what's available in the marketplace now. But what isn't as well known is what is the albedo of current roofs, right? So to know the increase attainable, you need to know what is out there now. And that was essentially what drove this project that I'm going to talk about today. The primary research question was, what is the maximum increase in roof albedo that's attainable in cities in California? So to answer that question, we needed to characterize the current stock of roofs at the city scale in California. There are ways of measuring the albedo of rooftops using handheld instruments called pyranometers, and you go under rooftops and you measure it. The issue is that to understand the roof albedo at the city scale would be really prohibitive using a technique like that. And so that led us to the idea of using remote sensing to understand the current albedo of roofs in cities so that we could look at a larger geographical region. So when we started this project, what we first thought of was using potentially satellite products. NASA has several free products that are available. One of them is actually an albedo product that is derived using their MODIS sensor. The issue with using satellite data like that, though, is that the spatial resolution is quite low. It's on the order of 1 kilometer, and so you can't make out the difference between a building and a pavement and a tree and things like this. There are commercial satellites, shown with the number 2 here, that are much higher resolution, actually. So these things can see 1 meter or even finer resolution. The issue there was that they cost money to acquire this imagery, and it was prohibitively expensive for the areas that we wanted to analyze. Orthoimagery was something else that we thought of, and orthoimagery is acquired often using airplanes. Because it's at airplanes, then they're flown at lower altitude. The spatial resolution is usually much higher. But the issue with that is that it's basically photography. It's not really scientific data. It's not radiometrically calibrated. Another issue is that, and I'll go into more of this in a little bit, but to really be able to derive the albedo of a material, you need information not just in the visible part of the solar spectrum, which is what our eye sees, and what is usually what photographs will acquire, because of course we care about what we can see for a photograph. But about half the energy from the sun is in the near-infrared part of the solar spectrum, which our eye doesn't see. And orthoimagery, for the most part, doesn't have any information in the near-infrared, though not in all cases. The next thing we looked at was we found this very interesting program called the National Agriculture and Imagery Program, called NAPE. And what the NAPE program collects aerial imagery for actually states around the all states in the United States. Not every single year, but they kind of, it's sort of a patchwork data collection scheme. But aerial imagery in California is available for many of the recent years, in the last several years. This is at 1 meter spatial resolution, so plenty of resolution to make out the difference between buildings and pavements and vegetation. They acquire data in 4 spectral bands, and so it's not just in the visible, the red, green, and blue, but it's also in the near-infrared, so that's something we needed. And it's available for free from the USGS. The issue, though, is that the data as available for free is not radiometrically calibrated, and so essentially what that means is that it's, there's a lot of color correction and compression, which makes it so that it's not scientific data anymore. It's taking it to be a photograph. But after doing even more digging, we found that in 2009, the company that acquired the NAPE imagery, that was contracted to acquire it from the U.S. Department of Agriculture, they used a sensor that's often not used for acquiring this imagery. It's a radiometrically calibrated sensor shown in the figure on the right here. And it's very similar to sensors used on satellites that are then used to derive albedo products. So you're actually getting scientific information. And so what we did is we acquired the more raw sensor data before the NAPE program reprocessed it and added all the color corrections and things like that, and tried to use that to develop a roof albedo product. And that was basically that was our project. So this shows the spatial coverage of the data that we acquired. Our aim was to derive roof albedo for 7 cities in California. So our cities of interest were Sacramento, San Francisco, San Jose, Bakersfield, Los Angeles, Long Beach, and San Diego. And so we acquired imagery shown in these red or orange, or I'm a little bit colorblind, but whatever color that is, in those shapes there. And what I'm going to focus on in this talk is the results from 5 of those 7 cities. So I'm going to leave out San Diego and Sacramento for reasons that I won't get into that much, but it has to do with the fact that we couldn't get citywide building outlines for those cities, and you'll see why that's important in a moment. We did get sort of city average mean albedos for those cities, but we didn't get the albedo of every single building. And this will all make sense in just a moment. So this figure here shows an overview of the approach that we developed to get from the remotely sensed data that we acquired to the mean albedo of each roof, which is what we wanted. And so this gives kind of the high-level overview, and then I'll go into some of the details in the subsequent slides here. So what we start with is on the top left up here. This is the remotely sensed radiances for these 4 channels or 4 bands that I told you about. And so what this tells you is basically at the sensor on the airplane, how much light is reaching the sensor in the blue, green, red, and near-infrared. And so what we wanted, though, was the amount of light reflected at the surface, right? Not the amount of light reaching the sensor. And so what you have to do to get from one to the other is essentially account for the various pathways for light between the ground and the sensor. And so that means that you have to make a correction for the various pathways for light in the atmosphere. Bright light can be scattered and absorbed in the atmosphere. It can be scattered into the sensor, even if it's not originating from the surface. It can be scattered away from the sensor, even if it does originate from the surface. And so that's called an atmospheric correction. And then also what we need to account for is the fact that reflection of light is not equal at all viewing angles from the surface. And so that's called accounting for surface anisotropy. After doing that, we essentially get remotely sensed reflectances for all pixels within each city. And again, in these 4 channels, the blue, green, red, and near infrared. And at that point, because what we're interested in is the albedo of roofs, we essentially extracted the pixels that were roofs. And to do that, we used building outlines that we acquired from various city governments around the state. And this is what I was referring to before, that we didn't get those for Sacramento and San Diego, so we had to use some other techniques for developing those building outlines ourselves. And I'm not going to go into that today, but it's detailed in the papers. And once you do that, you get what we have here at the top right, which is remotely sensed reflectance for just roof pixels now, not all pixels. The next thing to do is what we ultimately want is the albedo and not these reflectances in these 4 channels, blue, green, red, and near infrared. And so we developed an empirical model to get us from these 4 narrow band reflectances to what is known as a broadband solar reflectance, right? It's more characteristic of the amount of light reflected over all wavelengths for the sun, not just these 4 wavelength bands. Again, that should be a little more clear in a couple slides from now. Once we have that, then we did a bunch of ground measurements on rooftops using the pyronometers that I talked about before to essentially ground truth and calibrate our data. At that point, what we have is calibrated albedo data for all pixels within each rooftop. And so what we do is just average all the pixels within each roof, and we get the mean albedo for each rooftop in each city. So this shows an example of what the pretty raw sensor data looks like. It shows the 4 bands that I talked about before, the blue, the green, the red, the near infrared. And so anything that you see, for example, on the top left with a bright color means that it's reflecting a lot of light in the blue. If it's dark here, it means it's absorbing a lot of light in the blue, and so on. One thing that's kind of interesting to look at and shows why this NAEP program collects the near infrared band too, and not just the 3 visible bands, is that if you look at this kind of squiggly line on the right-hand side of each figure, that's a river that's covered with a tree canopy. And you can see that in the 3 visible bands, the blue, green, and red, it looks quite dark, right? And so that means it's absorbing the vast majority of visible light, but it's extremely bright in the near infrared. And so that's how the NAEP program and how it's an established technique for identifying vegetation in remotely sensed imagery. It's basically comparing the reflectance in the near infrared to the visible, because vegetation is pretty smart and it doesn't need near infrared light, so it just reflects it away rather than having it heated up. And there are actually cool roofing products that kind of mimic this in a way. They absorb in the visible, but then they reflect in the near infrared as a way of increasing the albedo of the product without changing the visible appearance of it. And so there are some products, especially for residential homes, where you see the roof from street level, and you want a cool roof without it looking like a cool roof that mimic vegetation in this way. So this is now showing you extracting roof pixels using building outlines. The base imagery here is actually not the imagery shown in the last slide. It's higher resolution, just so you can see the building outlines a little better. But what's shown in the orange shaded regions is essentially filled in versions of the building outlines. And so what we do is use these shaded regions shown here to extract the pixels that are rooftops. And again, we were able to acquire building outlines like this at the city scale from 5 of the 7 cities that we are interested in. And they're actually pretty readily available in most of these regions from city GIS departments, which made our life, well, easier than it would have been if we hadn't had this. I'll just put it that way. This is probably the most difficult slide to explain, so bear with me. I'll spend a couple minutes on it. What's shown on the left here is the imagery that I showed you a couple slides ago. So this is the imagery that's sensed via the sensor on the airplane. Now, the plot on the top right, that's showing you both reflectance and irradiance from the sun versus wavelength. So you got wavelength on the bottom axes. And first, just look at this, the thin black line that's labeled spectral irradiance. The corresponding vertical axis is on the right side here. This is the irradiance from the sun. And so what you can see is on the left-hand side of the plot, you have the irradiance here from around 250 to 400 nanometers or so. That's the UV part of the solar spectrum. The portion from 400 to 700 nanometers, that's the visible part of the solar spectrum. And then you've got all of this irradiance in the near-infrared part too, from 750 out to 2500. This is showing you why half the energy from the sun is in the near-infrared part of the spectrum. The next thing to look at is what is called the spectral reflectance of 3 example roofing products here. So these are the 3 lines labeled A, B, and C. And first just look at the line that's labeled B. What this is showing you is the amount of light reflected by the roofing product at each wavelength. And so you can see that this line B in the UV part of the spectrum, it's absorbing the vast majority of UV light. That's a good thing because, of course, I mean, this is the Air Resources Board after all, and UV light is the actinic flux that can create ozone. And so the good news is that cool roofs actually absorb UV, they don't reflect UV. That's a question that often comes up. It's because of the titanium dioxide used as a pigment in the roofing product. As you go into the visible, you can see that line B here, this white membrane, reflects roughly 90% of incoming sunlight, so the vast majority of it. It's not super wavelength dependent in the visible, that's why it looks white and it's not a color. And then you can see the reflectance starts to fall off as you go into the near infrared, but luckily it's mostly, these are at wavelengths where the sun doesn't emit that much, and so it doesn't contribute to the overall albedo. What the overall albedo actually is a average of this line here, of the spectral reflectance. So you're getting sort of an average sense of the reflectance of the product over all wavelengths. What the sensor actually measured, the wavelength ranges, is shown on this plot now in the blue, green, red, and the yellow is the near infrared, right? That's what's actually measured. And so what we need to do is come up with a way to essentially translate these 4 measured wavelength regions into something that's indicative of the average of this entire line here. For example, I guess it's a curve, not a line, but the curve labeled B. And so you can see that the visible ranges shown in the blue, green, and red actually make up the vast majority of the visible part of the spectrum. One of the challenges associated with the project was to make this kind of narrow wavelength range here for the near infrared, right? It represents a relatively small portion of the total near infrared wavelength range. So what we did was we measured in the lab these spectral reflectances of many, many roofing products, actually 100, I think it was 190, almost 200 roofing products that are representative of what we have here in California. And we came up with a way to relate these 4 narrowband ranges to the weighted average of the various curves that we developed for the spectral reflectance. So this is showing just a little photo of the lab testing and some of the roofing products that we tested. So lots of shingles, of course, in California, lots of tiles, both concrete and clay, various membranes of different colors, etc. And what you can see in the end was the empirical model that we developed was able to very accurately actually predict the albedo, so that's shown in the vertical axis, using the 4 remotely sensed ranges to what's labeled on the horizontal axis, the broadband albedo. So that's what you predict by taking the mean of this curve here. And the points on the plot show the relationship between the two. distinguishing by the type of roof that was measured, and you can see that the RMS difference was around 0.02. That's using albedo units that range from 0 to 1, so it's basically 2%, which is quite good. This is now a photo showing some of the ground truthing that was done. This is Pablo Rosado modeling a white roof on his head. He was on a rooftop here. I think this was in Los Angeles. And these rooftop measurements were used to compare the actual albedo at the ground level to the remotely sensed roof albedo that we derived. Okay, so up till now, I presented results on most of the methodology that was developed, although there are some more details in the papers, of course. And that is on the first paper that I put on the first slide. And now I'll talk about the results, which is on the second, published in the second paper. So what we get in the end is something that looks like this. We get the mean albedo of every rooftop. And this is zoomed in to a portion of Los Angeles. And it shows the mean rooftop for each of these roofs, where the color scale is shown on the right-hand side. And so you can see in most of the bottom and the top part of this illustration, where you have colors that are dark orange or so, and so that means the albedo is ranging from 0.1 to 0.15, sometimes up to 0.2. And so that means that 80 to 90% of sunlight is absorbed by those rooftops. Those are mostly residential homes. And then you can see, the reason why we picked this region is you can see sort of a commercial district here too, where you've got a little more variation. And so you've got some of these dark colored roofs or low albedo roofs too, but then you also have some buildings that clearly have cool roofs because they're blue, and so their corresponding roof albedo is 0.6 to 0.7 or so. If you zoom out a little bit, this is showing an example of the results just for one city. This is Los Angeles. And the takeaway point really is that most roofs in Los Angeles have low albedo, right? So if you summarize all of these 1.1 million rooftops that we looked at into a histogram, you have what's shown on the top right. N is the sample size, that's 1.1 million roofs. The mu value there, that's the mean albedo of rooftops in Los Angeles, and that's weighted by the size of the roof too. So it's an area weighted average, and you can see that the mean is 0.17. So that's the average roof albedo in Los Angeles. Again, meaning that over 80% of sunlight is absorbed by these roofs. And so what that shows is actually the vast improvement that is attainable from using cool roofs. I mean, the vast increases in albedo at least. This figure here now shows the average results for those 5 cities where we got each rooftop within the city. And you can see that for each of the 5 cities, San Francisco, San Jose, Bakersfield, Los Angeles, Long Beach, the roof albedo ranges, or the average roof albedo ranges from 0.17 to 0.2. Bakersfield here shows the highest average roof albedo. We think that's probably because that city has seen the most recent development compared to the other cities, and so they potentially have the most deployment of cool roofs given some of the cool roof regulations that I'll talk about later. One of the nice things about the data set that we use too is that there were, the NAEP program does essentially acquires imagery twice for 30% of the area. And so that means that for 30% of the buildings, roughly 30% of the buildings that we had acquired albedo for, we actually had duplicate measurements. And so we could assess the precision error of the approach to see, if the acquired imagery led to this value on one day, but then that value of another day, we can see how close they are essentially. And so that is the histogram of the differences. It's called the scaled arithmetic difference in this case, which is the formula is shown on the right. It's basically the reflectance of the first data point minus the reflectance of the second data point divided by the square root of 2. And what you can see is this histogram of all the duplicates in this example city here for Los Angeles, but we did this for all cities. And there are around 1 million roofs in LA, and about 1/3 had duplicate imagery. So this represents the errors in around 300,000 roofs. And what you can see is that the precision error was actually quite low, meaning that the data set was precise. Right? If you take the RMS value shown in the upper right, which summarizes this histogram, the RMS difference between the two duplicates was around 0.02, so quite good precision. This is maybe the second most complicated figure to describe, and so I will take this one a little slow, but I'll give you the takeaway point first. The takeaway point of the slide is that most roof area in the cities that we looked at was comprised of small roofs. So there's a lot of little roofs and not that many big roofs. That's basically the takeaway point. The way we show this in this figure is by showing the area fraction smaller on the vertical axes than the roof threshold shown in the horizontal axes. And so it's easier to understand if I give an example. So follow this the gray line here. If you start out with a roof area threshold of 1,000 meters squared, and you follow the line up into the blue dashed line, that's Los Angeles, and then you follow it over to the vertical axes, that shows that roofs that are smaller than 1,000 meters squared make up around 80% of roof area in LA. So most roof area is small roofs. Now these figures are similar to the last one, but instead of showing roof area in the vertical axes, it's showing the mean albedo of those roofs. Right, so on the left-hand side, let's again pick this roof area threshold of 1,000 meters squared, follow it to the blue dashed line, and then over to the vertical axes. You see that roofs that have a area of 1,000 meters square or smaller, their mean albedo is around 0.15, so low albedo for small roofs. And this is, I mean, the vast majority of residential homes will be smaller than that threshold. The one on the right is similar, but it's showing the statistics for roofs larger than the threshold. And so what you can see here is that for roofs larger now than 1,000 meters square, the mean albedo in LA is 0.23 or so higher. And for some of the other cities, right, those larger roofs have even higher albedos. And so the takeaway point is in the title. It's basically that small roofs have low albedo, larger roofs have higher albedo. And that's essentially expected because of the regulations on cool roofs that have been in effect since really since 2006, that at least initially really focused on large commercial buildings that had flat roofs that you couldn't see, and so there were requirements for really high albedo roofs for those commercial roofs. Regulations for smaller residential homes have been a little bit slower to be required, and also the requirements for albedo are lower because you can see them and people don't necessarily want to have a really high albedo white roof on their home that's visible from the street level. I also want to mention that a really nice website was created by some folks at Lawrence Berkeley Lab. It was basically, I think it was the public relations group or something similar to that, you can go to. It's a public website, albedomap.Ibl.gov, and you can essentially visualize the data that we created for the 5 cities, Bakersfield, Long Beach, Los Angeles, San Francisco, and San Jose. And there's a lot of educational information here, so you can look at sort of the albedo of a roof, compare it to the city average, and you can learn some things about the science and why it matters on the right-hand side of the website. So check that out at your convenience. So the policy relevant conclusions, I think, for this research. The first one is that many commercial and residential buildings in California have roofs that could be made cooler or more reflective to save energy. I want to make sure to emphasize that the imagery that we acquired, I mean, this project started several years ago, and the imagery is from 2009. So this is, you know, there have been a lot more cool roofs that have been adopted since 2009. But still, you know, I think the first takeaway conclusion is that many commercial and residential buildings in California have roofs that could be made cooler to save energy. From more of the urban temperature side of things, the first policy relevant conclusion shown in the second bullet is that buildings with small roofs, these are primarily residential homes, they constitute a really large fraction of the city roof area, and they have very low albedos. And so if the goal is to increase the urban scale albedo for either heat island mitigation or climate change adaptation, or however you want to think of it, you really need to include cool roof requirements for residential buildings where appropriate, and of course while maintaining desired aesthetics, because you simply can't increase the citywide roof albedo by focusing only on commercial buildings. They make up too small of a fraction of total roof area. So what are some of the latest policy developments for cool roofs? One of the most interesting ones is that Los Angeles recently became one of the first cities at the city level to require cool roofs on residential buildings. And so there was a very interesting workshop that was held in LA a couple of years ago, put on by folks at an organization called Climate Resolve that brought together scientists and policymakers. The mayor of LA at the time was there to talk about cool roofs, and preliminary versions of these results were shown there. There were many other scientists there showing their research too. And one of the, it was kind of incredible to me, seemed like a direct outcome of the workshop, is within 8 to 9 months, the LA City Council passed this ordinance requiring cool roofs be used for residential homes. The other recent development was a 2013 update to Title 24, the California Energy Commission Code, that prescribes that cool roofs be used on non-residential buildings and some residential buildings. So the requirements are shown in the table here in the top left. The first 2 rows are the requirements for non-residential, so basically commercial buildings. On the top row, you see that the minimum aged solar reflectance is 0.63. So this is the albedo required after accounting for the reductions that occur, after deposition of pollutants onto them and things like that, after they've been out on rooftops for years. And so that's an increase to that minimum albedo requirement from the previous version of Title 24. And that's for commercial low slope. So you can't see it from street level, basically. For commercial or non-residential high slope, where you can see it from the street, the albedo requirements are much lower, 0.2. And then for residential, that's shown on the bottom 2 rows here. You can see for low slope residential, you have the same requirement as the non-residential, except for that it's only in climate zones 13 and 15, and not for all climate zones as it is for non-residential. And so that means that you can see climate zone 13 on the map to the right is the southern part of the San Joaquin Valley, and then climate zone 15 is kind of the southeastern desert regions of California. For residential high slope, so these are ones that you can presumably see from the street level, the requirements are lower, 0.2 or so, and those are for climate zones 10 through 15. So the San Joaquin Valley, Sacramento area, parts of the sort of eastern portion of the Los Angeles basin. And I want to finish up by talking a little bit about some current and future work that's related to this project. The first is a project entitled Life Cycle Assessment and Environmental Co-Benefits of Cool Pavements. This is sponsored by the California Air Resources Board and is a collaboration between Lawrence Berkeley Lab, my group at USC, UC Davis, and PE International. And the basic idea is to really have a full picture look at the potential impacts of cool pavements, both from a life cycle emissions point of view, from a local climate consequences point of view, an air quality point of view, and a building energy point of view. And the results of this work are culminating in a policy tool where the finishing touches are just being put on it, so that folks can go and kind of play with the policy tool and do some what-if scenarios to see the environmental impacts of adopting cool pavements. Another project that I'm excited to say I found out was funded a couple of weeks ago is a project sponsored by the National Science Foundation, led by my group at USC, and in collaboration with Dave Saylor at Portland State University. The focus of this work is going to be determining optimal urban heat mitigation strategies for vulnerable populations in a changing climate. The idea here is to think about the climate and thermal comfort impacts of heat mitigation strategies really more at a micro scale, a micro-meteorological scale, rather than at the meso scale, which is largely what's been done so far. And you can see some preliminary results where we're modeling the microclimate of a neighborhood shown in the upper left, and El Monte, which is in the east part of California, and it gets extremely hot in the summer. I heard from Ash at lunch that he used to work in El Monte, so he must know the area well. And so the idea is to think about the optimal ways of deploying urban heat mitigation strategies at the scale at which they will probably actually be adopted in reality, and to think about the vulnerable populations that need some of these heat mitigation strategies, those that are the most susceptible to extreme heat in essence. So the elderly, people that don't have air conditioning, things like that. There's another upcoming project funded by the California Energy Commission through the EPIC program. It's another collaboration between Lawrence Berkeley Lab and my group and Haider Taha at Alto Stratus. And we're going to set up a urban heat island monitoring network in the Los Angeles basin. That hasn't quite kicked off yet, but will extremely soon. I'm looking forward to that one. And the last one is a project, again, funded by the CEC, and as a collaboration between Lawrence Berkeley Lab, my group at USC, and Jan Kleisel's group at UC San Diego. And for there, we're going to be looking at solar reflective cool walls, looking at the various building energy savings that can be attained using cool walls, thinking about the co-benefits to the environment, so climate benefits at really more at the micro scale for this one, looking at some photoactive materials that can potentially reduce local air pollution. We're going to be assessing the technology that's available now and trying to set up somewhat of an infrastructure that's similar to that for cool roofs, which is, there's a rating system now for cool roofs that's the Cool Roof Rating Council, and so setting up something similar for cool walls. That does it for my talk. I want to thank you very much for coming, and happy to take any questions. Yeah.
Oh, thank you. Two things came to my mind. What's the effect of urban forest, and in particular deciduous trees could reflect more in the infrared in the summer, and then let some warming occur during the winter. And I don't know if that's something you encountered in your study. And then the other part is covering roofs with solar cells. Seems like it's black stuff.
Seems like, what was the last word?
The solar cells are really black and very absorbing.
Black, yeah.
So
Right. So for the first question, we didn't really look at the albedo of vegetation. And we also couldn't look at annual cycles at all because all this imagery was taken in the summer, so we wouldn't have been able to identify, what's deciduous and what's not. The other thing is that, the stuff that I showed on the mapping of the four narrow, remotely sensed, reflectances to the broadband reflectance or the albedo, that we focused on roofing products for that, right? And so we didn't do any kind of similar mapping for vegetation. So, that's, yeah, so, right. So we were just looking at rooftops there. But yes, the albedo of vegetation in general is not all that much different from, let's say, warm roofs. So the benefit you get from vegetation or urban forestry is not as much from the albedo, it's really from the evapotranspiration that you get when you add vegetation. For the second question for solar cells, so really when you get to thinking about solar cells, you need to think more about the absorbance rather than the reflectance, which is one, the absorbance is 1 minus the reflectance, and then you account for the efficiency of the cell, so the amount of energy that's converted into a useful electricity, right? And if you really think about the absorbance of a solar cell, you're better off with a solar cell than a dark roof because you're converting, right? Some of the best solar cells, I think these days have efficiencies of 20 to 25% or so maybe, right? So right there, you're not converting that to waste heat. You're converting into useful electricity, right? And then maybe 5% of it is reflected. But still, from an urban heat island point of view, you're better off with a solar cell than a, kind of a standard dark roof. You, of course, don't get as much light reflected away as like a white roof does, right? So if you're putting a solar cell on a flat white roof, you're going to be absorbing more light than if it were just the white roof. But then, of course, the important counter to that is that you're creating electricity and you're reducing CO2 emissions, right? So from a global CO2 emission point of view, that's an extremely important thing. So there's a little bit of a local heat trade-off versus, global CO2 emissions. But, of course, lowering CO2 emissions is very top priority. So, implementing solar cells is certainly a good thing.
I have a question for you. In the project, you estimate or projected the albedo for the whole city, right?
Mm-hmm.
And will you able to use that number turn to a dollar amount in terms of energy saving? And follow up on that is you give the example for $167 20% saving. That's one slide for the two houses. Was that number adjusted for because it's a dollar amount, right? We're using electricity for cooling, but are they using electricity for heating or they're using natural gas for heating?
That's a good question. Ronan was the the group lead on that study, and he's on the line, so he can answer that one in more detail about what the heating level was. But in general, yes, it's actually relatively straightforward to convert albedo increases to more city level potential cost savings. Ronan has a paper that came out, I don't know, maybe 5 years ago or so, that actually did estimates at the national scale for the amount of money that you could save using cool roofs through the energy cost savings. And so those are things you can do. We didn't do that in this particular study. Ronan, if you want to chat about, if you want to talk a little more about that and
Sure.
the heating system used in those homes.
No problem. Can I be heard?
Yep.
Yeah.
Very well.
Excellent. All right. So maybe I can start with a question about the Fresno study of two side-by-side homes. So in that case, we were comparing both the cooling and the heating energy uses of the buildings, and we priced them according to the charges from the utility. And we was a full year study, including both the heating and the cooling seasons.
I think his question was, what was the heating system, the system in detail, was it natural gas or?
Yes, it was a natural gas furnace.
Yeah. Okay.
Yeah, thank you.
Sure.
Thanks, Ronan.
I was interested in how you used NAPE, when you use NAPE imagery to do your albedo assessment. Did you find any issues with the urban tree canopy or shadowing effects on these smaller, particularly like the smaller residential buildings of like 1 to 2 story?
Yeah, so that was somewhat of an issue. I mean, so and we talk about this in the paper, that what we were really deriving included anything that was over the roof, really, right? So it could have included some overlying trees. It actually can include even HVAC equipment and stuff like that too, right? And so we can't quite say that roofing material can fully replace what we're measuring, right? Because there's other stuff on the roof besides roofing material per se. So that was somewhat of an issue, of course, yeah, and something that we discuss in the study. An important caveat.
And as a second question, did you, any interest in looking at like thermal imagery to calculate albedo, maybe like 30-meter Landsat imagery?
Yeah, so thermal imagery tells you about the temperature, right? It doesn't give you information in the shortwave part of the spectrum because, right, and that's really what the albedo concerns. Okay. Given that the thermal emittance of roofing products doesn't vary all that much, there might be a way of kind of back calculating the albedo from thermal imagery, but I mean, my first order reaction is just that, you know, it's a different wavelength range and there are probably better sources of data for getting the albedo in the right wavelength range. But it's an interesting idea, though. Yeah.
Let me just also add one more issue to complicate things fundamentally further. We haven't talked about this because obviously this wasn't part of the study, but significant albedo improvements also indirectly change the radiation profiles of cities. And therefore they have a very significant role, far significant than their energy savings and urban heat island mitigation capacity in basically being a geoengineering technology. So that's something we didn't talk about, but that's a very key issue about this. So there's just more benefits than just what you saw. And so that's one thing that we didn't talk about. And the other issue that we didn't talk about is that at their resources board and generally in the climate change community, our emphasis is towards densification. We want people to live closer and closer and closer together. So if there are more and more people living in closer and closer proximities, you're likely to, in some fashion, if you don't employ cool roofs, cool pavements, urban forestry, various other technologies, to exacerbate the urban heat island phenomena. So although we want the densification process because it lowers VMT, it lowers the CO2 profile of various other things, we sort of need these kinds of technologies to actually make it work properly. So let us all thank Professor Ban-Weiss, and if you have any further questions.
Sorry. I was very curious to see the curve of the roof size in San Francisco being so different about all other cities. Could you comment on that?
Yeah, I mean, that's San Francisco is made up of a lot of, I don't know what to call them, but sort of two-story Victorian style, tall, sort of larger homes, right? And so that's the way San Francisco is. It's interesting that it's quite a bit different there, right? So you get a lot less of the sort of single-family house type of thing there, and it's more of the you get this rows of housing where they share walls and all this kind of stuff. Yeah, that was really interesting to see that too. I thought too. Thank you.
All right.
Thank you very much. I have a question that you may have heard before, but I haven't heard an answer to. Is your sense, having dealt with a lot of roof albedo issues, that it would be possible to detect building use in some cases? For instance, a refrigeration facility where the interior of the building might be, say, a sub-freezing temperature. If you're somehow measuring that roof, is there any way to detect the use inside?
Not with the albedo, because the albedo is really, I mean, the source of shortwave radiation that we're looking at is the sun, because it's so hot. And
I mean, if you were able to combine it with somehow getting a measure of the temperature, I'm not sure if you get that with the IR.
Yeah, so you get the temperature, but it's not with the near infrared that we're measuring, it's with the far infrared is where you get temperature. So it's a different wavelength range than we're looking at here.
What about detecting the use based on, imagery? You're have a way to isolate rooftop from surrounding imagery. Are you aware of any sort of pattern recognition that would analyze images of roofs to try to analyze the use?
I am not really.
Hi, this is Ronan. I could throw in something if you like.
Sure.
So It's true that if you were to have a real-time source of thermal infrared imagery, you could possibly draw some inferences about the temperature of the building. And if you had information about the albedo of the particular building, you could probably go a little bit further. But I would point out that most buildings, if they're conditioned, well, the temperature of the building is pretty much independent of the use because it's controlled by the HVAC system, which in turn is controlled by a thermostat. Things that are particularly unusual, such as a refrigerated warehouse, which have exceptionally low temperatures, could possibly show a different thermal signature, but such buildings are also very heavily insulated. So my guess is that the temperature inside the building wouldn't show up very well in the signal of the temperature of the outside of the building. So pure speculation, but my thoughts.
Yeah, one of the things that I learned really a lot about during this project is the vast amount of GIS data that's available too, and a lot of the data sets we used to, that had the building outlines would actually have some indication of their use too. So is this for emissions inventory development, or?
I'd be interested to hear more about those data sets.
Yeah. I can talk with you about that afterwards, because they will oftentimes give you quite good information.
Can I ask a question about the trade-off in different materials for roofs? There was a graph showing a pretty marked difference in reflectance for metal roof versus, I'm not sure the proper phrase, sort of a synthetic high albedo roof.
Yeah, like a white membrane.
Right. Are you aware, maybe a little more broadly, of the trade-offs between those, both in terms of winter, the heating cooling trade-offs, and also sort of longevity and
Yeah, so if what you're interested in is the building energy impacts, there are two properties that really define those. It's the solar reflectance, which is what this presentation was all about. And so, a white membrane that's extremely bright is usually the brightest, but there are also metal roofs that can be coated with a white coating that can be equally reflective too. The second property is the thermal emittance. Most roofs have pretty similar thermal emittance. There's one exception, which is actually what was shown here. It was shown in the figure as an exception, even though I didn't really go into that, but in the paper there's some discussion that metal roofs that are bare and not coated can actually have pretty low thermal emittance. So, and from a cool roof point of view, that's not a good thing. But really what you care about is the albedo. So anything that has a high albedo, it can be a white membrane, it can be a metal roof. From a longevity point of view, my understanding is that metal roofs have very, quite long lifetimes, potentially longer than a white membrane would be. Those white membranes are essentially plastic. They might have a lifetime of 10 to 20 years or something like that. And then another thing that's used with white roofing, we're talking about commercial here, is coatings. And so those can last, I think the average lifetime is maybe 5 to 10 years, so they don't really last as long at all. Metal roofs, I think are a lot less common for a commercial building with a flat roof, right? So a lot of times that could be used for a commercial building with a pitched roof or for a residential home. So, the roof products get used for different types of buildings, and then there are various trade-offs for longevity and albedo. But in general, albedo is the main determinant of the building energy effects, and then the different, longevities can impact, or the different materials can impact the longevity, which from an emissions point of view, plays a role too, of course.
And might also have some impact on whether, say, the viability of solar PV on a rooftop, or
whether or not you can install PV.
Which raises a question: could you make solar PV that has a higher albedo?
That's an interesting question. I mean, there's two responses to that. So I did a study a couple of years ago that looked at building integrated photovoltaics, and so this was essentially a white membrane that had film solar basically impregnated into it. And so that's a way of basically increasing the albedo while using a solar cell. There's a company that makes solar panels that they increase the efficiency. I think I'm remembering this right. They increase in the efficiency by having a highly reflective backing so that the incoming sunlight essentially has two chances to be absorbed in the solar cell, right? It can be absorbed on the way down or with the reflective backing, it can be potentially absorbed after that sunlight is reflected. So, you know, there is something with albedo and sort of the efficiency of solar cells there. But, you know, if you make a solar cell really reflective on the top surface, that's not good, because then you're reflecting the light away before it can be absorbed in the solar cell, right? So that's kind of a countering thing.
Sure. This reminds me of a question from the audience earlier that was going to be held over. I think it was a little bit addressed. I'm not sure if it was fully addressed. The question of whether there are materials for roof that actually sort of change their albedo summer versus winter kind of idea.
Yeah, so that's an interesting question. So there aren't really any available that I know of. There were a couple startup companies. I'm not sure where they are at this point, whether they kind of succeeded or not. But they were making materials that were designed in such a way that when the sun was high, right, think of it like a stair-step pattern, right? The material itself was like this. And so when the sun was high, like in the summer, what the sun was, you know, the light coming from the sun was seeing a high albedo portion of the roof. When the sun was low, right, it would see the other part of the stair like this, so that it was seeing a low albedo part of it. And so there are ways of toying with the design to get that kind of a thing. There are other materials that are called thermochromic or electrochromic, and those can be designed so that, you know, you can essentially change the albedo via electrical currents or via the temperature. But those, you know, I think one issue with that is that those are quite expensive, at least at this point. And roofing products in general, if you look at them, they're pretty cheap. I mean, people don't like to spend a ton of money on a roof, and so, you know, that changes that paradigm a bit.
I think with the metal roofs, there's a higher upfront cost, maybe with longer-term savings.
That's right.
I've heard.
Hi, this is Renan. I could throw in a few things when you've got a moment.
Sure, go for it.
Okay, I'll go back to a couple questions. First well, it's come up again now, metal roofs versus, I'll call them plastic roofs. So there is a difference in service life. Typically, the metal roofs are factory coated with the fluorinated polymer, white paint, and the metal and the coatings are quite durable, and you might be looking at something like a 50-year service life, depending. And as George mentioned, what I'll call plastic roofs, such as single-ply membranes, have a service life more like 20 years. As for the ability for either of those types of roofing to stay cool in the sun, what you want to look at is what we call the aged albedo. And fortunately, if you were to go to the rated products directory of the Cool Roof Rating Council at coolroofs.org, they have several thousand products for which you can learn both the initial albedo when first made and the aged albedo after 3 years of exposure. So there's an easily available metric that you can use to judge the consequence of your roof choice on the energy performance of the building. Next, for the question about photovoltaics, you could, in fact, at least in theory, design a photovoltaic to reflect at its surface the portions of sunlight that will be not at all useful for generation of electricity. And what those portions are depend on where the PV converts. So that is possible. I'm not sure if that's done. Most PVs do have that property that George described, which is a back panel that lets the light have pass through the PV on its way back up again. So that's a pretty common thing. It's true that a typical PV isn't hugely reflective to sunlight. It's probably absorbing something like 60 to 70% of the incident sunlight in a not useful fashion, that is, not reflection and not conversion. But I would point out that the PVs are usually either A, installed on a lot of insulation, if it's, say, a building integrated photovoltaic, which is going to reduce the thermal coupling between the hot surface of the PV and the interior of the building. Or the PV will be offset in that kind of installation, in which case there is an air gap between the back of the PV and the top of the roof. And if the back of the PV is a bare metal surface, then you have an air gap coupled with what amounts to a radiant barrier. The PV will serve to heat the city and to heat the planet, but it's probably not going to do that much to heat the building. So
one could conceive of changing that gap based on season. An idea just arose. If anyone has looked at solar water as something where you could tint the water black in the winter and tint it white, and I don't know if that would pencil out, but you can have a roof that's basically in a sort of a thin aquarium.
Yeah, there's a guy, I think his name is Russell. His name is Russell. I can't remember his last name, but he has an idea called bright water, where basically you would put micro bubbles into waterways and to make it more reflective. So one person has thought of that at least.
And his last name is Seitz, S-E-I-T-Z.
Right. Thanks.
Thank you. One last wild question. Are you aware of any effects on wildlife or vegetation from higher reflectivity?
I am not aware of any effects on wildlife or vegetation. Generally, rooftops are, at higher level, and so any reflected light is, of course, depends where it is, but it's not going to affect the amount of radiation that's seen by vegetation in general. Whether there's an influence on wildlife, I'm unaware, but I haven't heard of any.
Thank you.
Thanks.
Thank you so much once again. But there was still one more question.
I've gotten 4 or 5 rounds of applause here. Let's keep them coming.
Yeah, you're using the aged albedo for after 3 years. Does it tend to stay pretty much the same even after 3 years?
Yeah, so there are some studies that show that after 3 years, that's when it sort of plateaus, the solar reflectance, right? So the question was, a lot of the time we use a 3-year aged reflectance for a material as being sort of the aged reflectance. And so yes, it stabilizes after 3 years. The one caveat to that is that, right, if you have a white coating and let's say that you keep that same white coating on a roof for 15 years, it's going to basically disintegrate, right? So you're going to lose albedo that way if you don't actually properly kind of upkeep the coating, right? And there might be some situations where microbial growth can become an issue. It's not really an issue in California, but in humid regions, you might have more microbial growth after 7 to 10 years because of the way that the product has degraded and for example, leached plasticizers or something like that. But from the point of view of atmospheric deposition and leading to reductions in reflectance on a material, 3 years is basically, it's reached a steady state.
And does it matter if you wash it or sweep leaves off or do that kind of maintenance?
It certainly helps to sweep things. One thing actually that's interesting when you go and sort of get on rooftops and look at them is that the thing that seems to affect the albedo the most is when the roof is in a way improperly installed and you have areas of ponding water, right? Anywhere you have ponding water, that can lead to issues with the material itself, and it leads to a ton of biological growth that is very, very dark. Right, and so in a way, that's one of the hurdles to make sure that the roof is actually just properly installed and doesn't have a bunch of ponding water all over the place.
You might want to check George's mic. I can't hear anything.
Oh yeah, the batteries, but I think we're done, Ronan. Thanks for calling in.
Okay, so we'll be ready in a few minutes. All right, okay.